Can you hear me? I
Yes.
Okay, great. So thank you very much, and I'm greatly honored to be here. I'd like to give you a update on the classification program on counting problems. I hope the screens are actually all acceptable visibly. Can you confirm that this thing works? It doesn't seem to work. Do I have?
I can see the screen.
But I don't seem to be able to. Oh, now I can.
Okay.
Okay, very good. So I would like to start with the classes that were defined by Leslie Valiant, called the counting class number P. This is basically a counting version of NP. Every NP problem defines a counting problem. So for example, satisfiability asks for how many satisfying assignments are there in a given formula. The number set will then define the question of, given a Boolean formula, how many satisfying assignments are there. So you can think of any particular NP problem, Hamiltonian circuit problem, vertex cover problem, independent sets problem, coloring problem, etc. Every single NP problem, you can say how many solutions are there. And in fact, we'll see that often it's also interesting to ask questions like how many solutions with weights, and that the sum of weights of all solutions is usually the counting class. So for example, the number of perfect matchings, given the perfect matching, every edge may have a weight, and the product of the weights on the edges will then give you the weight of that particular perfect matching. And then the number of perfect matchings is a special case where every edge is weighted 1. And in general, you would have a sum of weights of perfect matchings. And then there are these number P complete problems, just like in NP. So for example, number perfect matchings, permanent, number satisfying assignments, these are all number P complete. I do have difficulty moving somehow. I'm going to go back to a little smaller screen, then it definitely works. Okay. So the classification program is trying to give basically a classification for every problem possible, as broad as possible, a class of problems. This is in fact not possible for the entire class number P. There's a version of what's called the Ladner's theorem. Basically says that for the class number P, there are strange problems that you really cannot classify them easily. The degree structure is undecidable and so on. So basically what we'd like to do is to classify in a very broad class of counting problems, that every problem in there you would like to classify as much as possible. And this is addressed in 3 frameworks called the graph homomorphisms, counting constraint satisfaction problems, and Holland problems. And we have made remarkable progress with many of the my coworkers and students. Some of them are actually, I think, in the audience. In particular, for example, Ping Yan, who has done fantastic work in this program. So I like to start with the first program, first framework called the graph homomorphism, and that was proposed by Laszlo Lovász from '67. And on his webpage, he has a special page called the homomorphism paper. This summarizes his own papers on this topic for the last almost 50 years. Yes, he proposed in 1967 when he was probably a teenager. So this is an abiding interest on his part. So here's an example. Suppose you have a graph called a triangle. Basically, you have 3 vertices and 3 edges connecting them. It's a case 3. The adjacency matrix is this H. Okay. By the way, when I move my cursor, does anyone see my cursor? Like H? I'm circling around H. Anyone?
You can see, yeah.
Yeah, okay, great. So this H then basically is the adjacency matrix of this triangle. And then the graph homomorphism from a graph G to the graph H is basically mapping from the vertex of the vertices of G to a vertex set of H, such that whenever you have an edge in G, it will map to an edge in H. It does not say that a non-edge in G must map to a non-edge in H. Okay. Now it turns out that this particular problem in a homomorphism language sounds very algebraic, but it's rather combinatorial. If you think about this H, it really represents a disequality function. So if you name the rows of red, blue, green, then 0 says that I cannot map an edge in G to two vertices which are named as red, or green, or yellow. Okay? It has to map to different colors. And this is recoloring, basically. Every edge, the two ends must be mapped differently. And in general, what you would have is a adjacency matrix of Q by Q. It has Q colors, for example. And it doesn't even have to be 0, 1. And then it defines a weighted binary edge function. So if you take a color I coming in and color J comes in, the IJ entry tells you the value. It could be 0, could be 1, could be something else. And then you're going to multiply these values together. In this particular case, it's just disequality function, a binary disequality function, and this gives the coloring problem. But you can define much more complicated functions. And so the product, if it's a 0, 1 case, it just says 1 if it's A mapping, that's a homomorphism, 0 otherwise. But in general, it will be a weight. And you sum over all possible values of the mapping of the product of the result. And that is called the graph homomorphism function. That was defined by Lovász. And the intent of that is to capture a very wide class of graph properties like the vertex coloring and independent sets and so on. So for example, here is an example where this is the adjacency matrix of two vertices. Between them, there's an edge, and then there's a loop at 1. And then a vertex cover means that I want to map the vertices of G to 0 or 1 in the target graph, such that whenever I have an edge, let's see, the vertex cover, I want to make sure that the vertices that map to 1 takes care of all the edges. Okay, so this is the vertex cover. And you can have something like this, which is, it takes a little doing here, but you can say that it's not just zeros, but the product will cancel in such a way that this can be shown to be equivalent to counting the number of induced subgraphs with even number of edges. So it turns out that, for example, this problem is actually polynomial time solvable for this partition function. In general, it will be sharply hard, and the classification theorem is trying to classify these partition functions. There is a long history of such partition functions from statistical physics. For example, the Ising model is defined by such a function. And you think about this e to the exponential of a sum. The exponential to a sum is really a product, so it's a sum of product. And this is viewed as the weight for a configuration in the statistical physics, and the ratio of this over the entire sum is the probability that you find your system in that particular configuration. So this comes from statistical physics called the Ising model. And there are a whole host of other such models where the Ising model is basically represented by this. And then you have the hardcore guess model, for example, the Beach model. And so for example, the Beach model will be a 4x4 matrix with a loop. So there are non-zero entries at 1, 1, 2, 2, 3, 3, 4, 4. And then there is non-zero weight at 1, 2, of course, then 2, 1, 1, 3, 2, 3, and 3, 2, and 1, 4, and 3, 4, and 4, 3. So this, and if you were to map your edge to 1, 3, or 1, 4, then this will kill it. It's a 0. Okay, so this is things like that coming from statistical physics, as well as the Lovász graph homomorphism framework. And to this, the very first theorem is due to Dyer and Greenhill. It says that if I give you a matrix A, that defines the problem, that's a 0, 1 symmetric matrix representing the graph homomorphism problem, then this problem is either in polynomial time, means that if you give me a G, the computation of this function on G will be computable in polynomial time in the size of G. A is part of the name, defines the problem, like it tells you this is the coloring problem, or this tells you it's the vertex cover problem. it's part of the definition of the problem. G is the input to the problem. And for the given input G relative to its size n, the computation is either in polynomial time or number p hard. And that is the dichotomy theorem. That's of Dyer-Greenhill for the 0-1 case. Bulatov-Groh proved that if the matrix A is non-negative, then there's a similar such theorem. And this was then further extended by Goldberg et al. To the real valued case. And this is a huge jump because once negative values occur, there are possible cancellations. And the cancellations, just like the determinant, is at the heart of lots of efficient algorithms. And to the complexity classification theory, this is the obstacle, because this may be that there are very clever algorithms that you don't know. And classification theorem says basically that these are the ones that we know and there's nothing more to know. Okay, so this is what basically the classification theorem is trying to achieve. This was finally achieved to the complex case with Ping Yan and Shi Chen. Okay, so this is the graph homomorphism dichotomy. And our paper appeared some time ago. It's a pretty long paper because it's a long sequence of derivations have to deal with all possible matrices. Okay, let's move on. It turns out that for the graph homomorphism problem, in the Dyer-Greenhill original paper, which was in the 0-1 case, they also proved that if the matrix A satisfies a tractability condition, then for every G, the problem is polynomial time computable. And if it doesn't satisfy the tractability condition, the A doesn't satisfy the tractability condition, then for arbitrary G, it would be sharply hard. But not only that, even for G of bounded degree, so this is the bounded degree case, for the bounded degree input G, the problem remains sharply hard. Okay, so this is a strengthening of their own Dyer-Greenhill theorem. The corresponding theorem for Bulatov-Groh actually remained open for about 15 years until with my current student Govorov and Martin Dyer, we proved this, that in fact it's still true. So, but what really the prize, of course, is the dichotomy on the complex case, not just non-negative, but not even for real, but for complex. So the dichotomy with Ping Yan and Shi Chen I just mentioned. And it turns out that this we have just achieved, and it will appear in Fox 2020. And it's a pretty long paper, and then the full paper is in the archive. It says the following. You give me a symmetric complex matrix, arbitrary size. The problem of the computing of the partition function, the input is a graph, and relative to the size of G, you compute this function, which is this exponential sized sum, but sometimes it can be computed in polynomial time if the A satisfies a certain condition. Otherwise, the problem is number p hard, even when restricted to the bounded degree graph G. So this is the theorem that is going to appear in Fox 2020. And so I will now move on to a different topic, second framework, which was the counting constraint satisfaction problems, counting CSP. Somehow it's not working again. Okay, so what is a counting constraint satisfaction problem? Well, it's defined by a finite set of constraint functions. Each one of them has a certain arity. So maybe the F1 is a binary function, arity 2. The second will be maybe a quaternary function. It takes 4 inputs. Each of the 4 inputs will take one of the Q colors. And once you give me these, my first input is red, and second is green, and third is red again, and fourth is yellow, then I'll give you value. Okay, so this is such a constraint function. And this constraint function then, this set of constraint functions then defines what's called a constraint satisfaction counting problem for the set. The input instance of such a problem consists of, you can imagine as a bipartite graph where the left-hand side are variables, n variables. Each one will take a value over the color set Q. And then on the right-hand side, there is a sequence of applications of these constraint functions on these variables. For example, F1 can be applied to X1, X2, and F1 can be applied again on X2, X3, and F1 can be applied to X3, X7, and then F3 maybe it's a ternary function x3, then you can be applied to x1, x7, x9, for example. Okay, so these functions f can be used many times. H is fixed. That's like the name of the problem. It could be 100,000, but it's a constant. Given this set of functions, then I will define a instance. I'll define the problem called a number CSPF, and this number CSPF then takes instances which are arbitrary n-sized bipartite graph. The left-hand side are variables, right-hand side are constraints. And each of the constraints come from this constant-sized constraint satisfaction problem. Okay? The graph homomorphism problem is the special case where you only have one constraint function, which is a binary symmetric, if it's the undirected graph. And then you will multiply or take the product of the constraint function evaluations and you sum over that. That's exactly the same as the partition function. Okay? And the counting constraint satisfaction problem has, again, a long history. In Craigno-Herman proved that if the domain, the number of colors, is 2 and the constraint functions take only 0, 1 values, then there is dichotomy. And this was gradually extended further and further down. Finally, with Shi Chen, we have the dichotomy for general domain and general set of complex valued functions. But there is an interesting twist here, that these are dichotomy theorem says that if you give me a set of constraint functions, so for example 75 functions, it defines a problem with these 72 functions, and the input is a n-size graph, and relative to n, what's the complexity of computing this partition function, and this complexity relative to n is either in polynomial time or Sharpe-Hart. But if I ask you the alternative question, that if I give you the 75 functions, which of the two cases it defines? So the 72 becomes an input. In that case, it is at the moment not even known to be decidable. The strongest one that is known to be decidable is the one with Pinyin and Shi Chen on the non-negative case. So this is an interesting, very stubborn open problem at this point. So the theorem is this. For an arbitrary domain, say 75 colors, for any finite set of functions of complex valued constraint functions, maybe 59 functions. First is binary, second is binary, third is 10 variable inputs, and so on and so forth. This problem defined by these 75 functions is either polynomial time solvable if the f satisfies a certain condition, or if it fails these conditions, then this problem is number PR, nothing in between. And when I said it's not known to be decidable part is to say that if I presented you with this particular set of f constraint satis functions, which of the two cases it did go, and that is not known to be decidable. Okay. I guess it's decidable, but we just don't know how to prove it. Okay. Now I want to move to another framework, which is even more general in some sense. It's a Holland problem, and this came from holographic algorithms. The definition is very similar, but the only thing I think you need to know is basically the variables now are on the edges. So you should imagine basically as the example of the matching problem. So let me show you how the matching problem is expressed this way. So the matching problem, everybody knows, is to pick a set of edges so that no two edges are sharing a vertex. And if every vertex has been covered by an edge, in this particular case the red edges, then it's called a perfect matching. It covers everything in a sort of packed way. Okay? No two edges share a vertex, and every vertex is covered by one. So the constraint at every vertex now is to say that among the edges that are incident to me, exactly one of them is 1 and the other are 0 in this choice. Okay? So you assign a constraint function at every vertex such that it is exact one function. And now you think about assigning 0, 1 values to the edges, which are the variables now, the domain 0, 1. You assign values to the edges in such a way that at every vertex, exactly one of the edges is chosen. And this is the perfect matching. So if you sum over all these 0, 1 assignments, multiply by the function I just described, this exact one function, and it will be 1, this product 1, if and only if at every vertex it sees one incident edge chosen. And that means it's a perfect matching. And the sum over all 2 to the number of edges, many assignments, some of them will be 0, some of them will be 1. Those 1s are exactly the perfect matchings, and 0s don't contribute. So this quantity, the Holland quantity, in this case, is the number of perfect matchings. Okay, and there's a theorem due to Friedman, Loas, and Scriver that shows that this cannot be expressed by the graph homomorphism world. And if you want to talk about matchings, then it's just at most one function. Now, let me mention that in some sense, the only thing known to be solvable in polynomial time for perfect matching is dominated by these two particular extremal cases. On the one case, you want to talk about existential questions, like, is there a perfect matching? And this problem is solvable by Edmond's famous algorithm for perfect matching of general graphs. It doesn't have to be planar, doesn't have to be bipartite. On the other hand, for the counting problem, there's a famous theorem due to Castellan that says that if you count the number of perfect matchings in a planar graph, it's polynomial time solvable. And so, for example, Jerem proved that even if you want to count all matchings, not necessarily perfect, in a planar graph or in a bipartite planar graph and so on, they are still going to be number p complete. So basically everything known to be solvable in polynomial time for matchings is dominated by these two, roughly speaking. Okay. There is this famous theorem due to Castellan, and it's called the Fisher-Castellan temporally because the three of them independently, Fisher and temporally was not independent, but Castellan was independent of the two. They gave this algorithm that is using what's called a Pfaffians, roughly it's a determinant, to solve on the lattice graph. And then eventually Castellan generalized this to general planar graphs. So it's the FKT algorithm, but it's the Castellan theorem. It says that for an arbitrary planar graph, if I want to count the number of perfect matchings, it can be solved in polynomial time. In fact, this can be done in weighted case, and then the theorem really goes for the weighted case. It uses weighted even if you don't start with weighted graph. Okay, but for about 50 years, this algorithm, the FKT algorithm, basically stood as the polynomial time algorithm for counting problems over planar graphs that are sharply hard over the general graphs. This is one of the most outstanding instances where something really fantastic algebraically happens that there's no sort of known combinatorial simple way of doing it. And then in 2001, Les Valiant introduced match gates, and using those to do what's called holographic algorithms. And this technique then extends the reach of this FKT algorithm to a number of other problems, and I'll mention a couple. And this has generated some general press, scientific press, scientific American scientists articles, and discuss about these kind of things that seems to be rather strange that you can do it in polynomial time. And it discusses some of my papers with Ping Yan, for example, on this. Let me just show you a couple of such problems that on the face of it doesn't look like it should be solvable in polynomial time, but it is. And this is the holographic algorithms using the Castellan's method. The problem is this: if I give you a planar graph with maximum degree 3, and I want to count the number of orientations such that no node has all edges oriented toward it, and no edges oriented away from it. In other words, there's no sink, no source of a planar graph maximum degree 3. Okay, these problems have a lot of historical motivations. There were contributions by Ising and Ansega. Ansega was a Nobel Prize winner. Fisher, Temple, you have seen them, Castellan, and C.N. Yan, T.D. Lee, Baxter, Lieb, Wilson. Here's another Nobel Prize winner. Oh yeah, of course, everybody in China knows C.N. Yan and T.D. Lee. This was a time when they were still friends and they still wrote papers together. Yes, but they did worked on some of these problems. There's a famous Lee-Yan theorem in this area. So here's an instance of a typical case where I give you such a graph, and every vertex has degree 2 or 3, and I want to count the number of ways I do these orientations. And these orientations are such that at every vertex, for example, here, one thing in, 2 arrows out. Okay? And somewhere here is 2 arrow in, 1 arrow out, and so on. So you want to count all such valid orientations. And it comes from statistical physics and trying to look at the partition functions, the order number of orientation configurations, and so on. I don't want to go into too much into that, but these problems, it appears that you're talking about exponentially many different ways, and how are you going to do it in polynomial time. But it turns out this, by the Castellan's algorithm, a variance holographic transformation with match gates to the Castellan's algorithm can be solved. And this mysterious situation seems to beg the question, and this is a quote from Leslie Valiant. It says that, this of course several years back, it says that the situation with the P and the NP question is not dissimilar, and here's a very typical British way of putting it, is not dissimilar to that of other unsolved enumerative conjectures in mathematics. The possibility that accidental or freak objects in the enumeration exist cannot be discounted. And indeed, if any of these so-called freak objects exists in this framework, it would have collapsed number P to P. And so this begs the question of whether our belief in number P not equal to P or NP not equal to P is that well-founded, in the sense that we haven't examined all these things thoroughly. And just to give you an idea of what kind of match gates, how complicated or how sort of fantastic could look, you could have things like square root of I appearing, and this way it implements a certain function that we need in the holographic algorithms. So you can just say, oh, such things don't exist. But if you don't actually know such things actually could exist, it's a very feeble, intellectually not a very substantial claim that therefore I believe not P is not equal to NP or sharp P not equal to P, right? Why? Because you haven't seen algorithms that solve number P hard problems, right? But here are the type of algorithms that use this sort of objects. You haven't seen them yet. So, okay. So I'll just stop here by saying that this certainly throws into some doubt, like what the Valiant's quote is suggesting. And so it begs the question, and this was basically the starting point where we and Pingyan and Mingji and Shichen and my other students, we embarked on this 10 plus years of effort trying to somehow bring order to chaos, if you will. We like to give a complete, clean picture of these things when it is in polynomial time, when it is not. And we like to have, short of settling P not equal to sharp P or P not equal to NP, we like to say that all the problems will be either solvable this way or not if P is not equal to sharp P. Okay. And there's a long sequence of nice dichotomy theorems on the Holland problems, but most of these work has been on the Boolean domain. And I must say that almost all the deep progress, I shouldn't say, with few exceptions, most of the work has been on the Boolean domain in the holographic algorithm, the Holland problem dichotomy. So, for example, the work by Jia Bao and Professor Wang Hanping, it talks about the non-negative Holland on the Boolean domain. There are a couple of results that were talking about higher domains. For example, there was one work with Pingyan and Mingji. We gave a domain 3 single ternary symmetric constraint dichotomy. With my student Guo Heng and Tyson Williams, we used some Ziegel's theorem and Galois theory to prove certain dichotomy for a very restricted but arbitrary high domain Holland problem, including the edge coloring problem. That's actually was open for several decades. Yeah. So this is a nice outcome of this. The one thing I like to report in our most recent progress is a work with Shao Shuai. He's really a brilliant student. This is a dichotomy for all real Boolean Holland problems. And this will appear in Fox 2020. It says this: if I give you an arbitrary set of real-valued constraint functions, there is an explicitly specified tractability condition, such that if f satisfies it, then the Holland problem is polynomial time computable. Otherwise, it's number p-hard. And the criteria is also easily decidable. I certainly, with the length of this paper, I really cannot go into its detail, but I like to give you a little flavor because I think there is something very interesting that we may get in touch with certain quantum information theory or quantum computing. I'm no expert in that, but I can smell there's a huge potential intersection here. So it's a potential new vista, and I would like to encourage people who are in this area, who are much more expert than me on quantum theory, to look into that. So in particular, we encounter two special functions. One is called f6, one is called f8. And I give you a nickname. The f6 is called the Lord of Intransigence. The reason is because it gives us tremendous trouble, and the f8 even more. Together, they probably stopped our progress for about 2 years. Often we thought we have done everything, but these two always gave us trouble. So this is a function, it's the constraint function. It takes 6 variables and it has 64 entries, 2 to the 6. And these are the functional values. And another way of looking at it, this picture, is that these are the -1 entries, these are the +1 entries, these are the 0 entries. And this particular function has enormously interesting properties that are related to quantum computing, I would say. And let me mention another one. I'm running tight in time, so I want to be brief here. But let me mention the Queen of the Night function, which is the 8th variable function. It has a very intricate group of symmetry on these 8 variables, and it's defined as follows. It's 8 variables of Boolean input, and the first 4 sum to 0, the last 4 sum to 0, the first 2 of the first 4 and the first 2 of the second 4th sum to 0, and then the odd part sums to 0. Now, of course, you can see this sums that, gives all the sum equal to 0. So if the odd all sum to 0, the even also sum to 0, and so on. So there are many different ways to express this, but these are the independent equations for this function. Another way of saying is that I can take the x1, x2, x3, x5, and this is not a typo. I put a red here. I mean I cannot take x4. I must, in this definition, take 5 as free variables. And then the other remaining 4 variables will be the 4 choose 3 mod 2 sum of these variables. Now, of course, these 4 can be arbitrary 4, except if you choose arbitrary 3, there's a 1 that is excluded. So if you take x7, x8, x5, then there's exactly 1 variable, in this particular case it would be x6, that is excluded. You cannot choose that. But then you can choose any other of the 4 to make the 4 free variables. Okay? And then the other 4 dependent variables will be the subset choice of the 3. Now, this still sounds very abstract, but there is a very interesting subgroup of S8 that is the symmetry group of this. And this is how the matrix would look like. The dotted ones are 1s and the others are 0, so there's very sparse. But it has these very fantastic derivative properties. And I am not even going to define what is a formal derivative here, but we have derivatives that are sort of making just a little twist that wouldn't be what you expect. And these B up there are what's called the Bell signatures. These are the ones that came from quantum computing called the Bell signatures. If you take the derivative against any 2 of the 8, and there are 8 choose 2 possibilities, so there are 7 times 4, 28, you will get the properties which are tensor products of functions on these variables. And if you can see that if I take 1, 2, the derivative, 3, 4, and then exactly one of them is not appearing. How do I put this way? If you were to imagine this thing is the tensor product of of functions on 1, 2, 3, 4, 5, 6, 7, 8 respectively. Then when you take the 1, 2, you get the rest. When you take the 3, 4, you get the rest. But then if you take the 1, 3, it would be the 2, 4, but then the 5, 6, 7, 8 should remain, but it doesn't. It twists. It becomes the 5, 7, and 6, 8. So I don't have time to go into explaining all this table, but this is a fantastically interesting sort of some symmetries going on that is not appearing in the simple Bell state if you are in quantum. This is a higher Bell type state that I think a lot of interesting properties one will someday that someone will really understand everything about this. All we did was basically we managed to overcome these difficulties and get the dichotomy theorems. Okay. Let me mention that for the planar case, we also have the dichotomy. This is a work with for planar Holland with Zhi Guo. It says that now I have three cases. You give me an arbitrary finite set of constraint functions of the Boolean variables, each taking complex values and not necessarily symmetric. Then the number CSP problem belongs to either polynomial time solvable or 2 and 3 together, that is in number P hard. But within the 2, 3 together, if you restrict to planar cases, then there's a subset of those F set that will be polynomial time solvable, but generally number P hard. And the remainder will be even number P hard over planar graphs. And the splitting of the two is exactly those which are Valiant's holographic algorithm reducible to the FKT Castellan algorithm. So this is a complete classification on the Boolean. And this is also a pretty long paper, about 100 pages. What it is claiming is that there is a universal method to solve such things on a number CSP type problems on Boolean variables. And this universality is not true if you look at the Holland problems. And this is a very strange situation because the Castellan's algorithm of perfect matching is really designed for a Holland type problem, but it is only universal for CSP, but not for Holland. Okay, so this is a rather non-self-evident fact. Okay, so at this point, I'd like to transition into a part of the talk where, according to Hendrik Lenstra, that a mathematical lecture without a proof is like a movie without a love scene. So I would like to give you a little peek under the hood of some of the proofs that I will present in such work. So the remaining part of the proof, the presentation will be a little bit denser. I hope you still get a flavor of this type of things, okay? So I am zooming into this 100-page proof with Pingyan and Xichen on the graph homomorphism paper, where we show that a matrix A of an arbitrary m by m size symmetric that either defines a polynomial time solvable graph homomorphism partition function, or it defines a Sharpe partition function. And the proof there is to stringently successfully putting on more and more stringent requirement on the matrix A that it must satisfy some additional conditions, otherwise it will be Sharpe hard. And assuming now it satisfies these conditions, it must be further satisfy some additional conditions in order to be, otherwise it will be Sharpe hard, and so on, until in the end, so much constraint so much beautiful properties has been proved that A must satisfy, otherwise it will be Sharpe hard. At that point, we say that if you have so much great properties, then in fact you define a polynomial time solvable problem. Okay, so this is like this bird's eye view at 5,000 feet or 10,000 feet of this 100-page paper. And I am now zooming in into one little section where I say that I already know that the A must be, or by some case, it must be a what's called discrete unitary matrix, as defined here. And then I want to say something more about it. Okay, so the discrete unitary matrix has the following properties: that every entry is a root of unity of some order, and this order is the least common multiple, the maximum order of these entries is the m. And it normalizes the first row and the first column are all 1, that's normalizing. And then every 2 different rows and every 2 different columns are orthogonal. Orthogonal in this ordinary dot product sense with the conjugation. Okay, so this is a typical standard definition of inner product in the complex case. So discrete unitary matrix example, you have this thing we said earlier was solvable in polynomial time. And this is actually also one of the things. If you do the dot product, you see you have 1, minus 1, minus 1, 1 again, so it could be 0. And this is like the Fourier type matrix, 1 plus fifth roots to the third, fifth roots to the minus third, and so on, adding up will be 0. So this is my examples of what's called a discrete unitary matrix. Okay, and what I want to prove to you is that it nevertheless will define a Sharpe-Hard problem unless it has some further beautiful conditions. And this further beautiful condition is that the rows and the columns must form a group, a mathematical group, in the following sense. That if I give you two different rows, I, J, it doesn't have to be different, any two rows, there is a row, K, such that if you entry by entry multiply, you get another row. So for example, in this case, if you multiply, you get 1, C to the 3. C to the 3 is actually C to the minus 2. C to the minus 3 is plus 2. Plus 1, 1. Minus 2 plus 1, minus 1 here. So if you multiply entry by entry of the second row with entry by entry of the third row, you get the fifth row. Now you say this is only closure of the multiplication in this Adama product sense, that you entry by entry multiply, you get another row. But because the orthogonality condition that every two different rows will be orthogonal, it must be a unique row. It cannot have another row that is identical, because then they would not be orthogonal to the product. Okay, so if you multiply this row with this row, you get the fifth. It cannot be the fourth as well, because the fourth is orthogonal to the fifth. So it will be a unique thing. And since the set of rows is finite, and this is a simple exercise in a finite group theory that says that I have a finite abelian group, and I have a closure property that if I multiply two entries, two elements of your set, I get another element in the set. And I have also the first row, which is all 1, that is the unit element. Then it's enough for me to say that it's a group. There must be inverse. Okay, so what's the theorem? The theorem says that if I start with a symmetric M discrete unitary matrix, this problem is either going to be hard, or it must further satisfy this condition. And this will be a one big step towards showing that then the next theorem says that let A be satisfying the A matrix that satisfy the group condition, then it must be hard unless it has some other conditions and so on. So eventually, so much conditions on it, it will say that this problem is going to be polynomial time solvable. Okay, so that's how the proof would go. So we are going to focus on just this theorem. Starts off with discrete unitary, proving that it has group property. Otherwise, it will be Sharpe-Hard. And as we often do in this case, we design what's called a gadget, and this is a graph. And the idea is that you have two vertices, U and V. They are going to be plugged into your graph and replacing a current edge that's between U and V by this gadget. And you're going to have sort of wheel of set of vertices, C1, D1, C2, D2. And you're going to have, if P is not just 2, you have a C3, D3, C4, D4. And the relationship of Ci, Di relative to the U and V and A and B in the middle are exactly the same as described here. These thick ones are going to have multiple edges. And remember, these entries of your matrix are roots of unity of order m. So if I have m minus 1 powers of the root of unity of order m, they give me inverse, or conjugates. So this basically will produce conjugates. And what we do is replacing every edge by this gadget. And once I do that from the graph, I get a new graph called a G to the P. And it is easy to see that I have a relationship that says that for a certain matrix defined by this gadget, for an arbitrary G coming in relative to this, I will get the partition function expressible as the original partition function on the graph that I just changed. You don't have to really read this too much, but the only thing I want to say now is that now there's a reduction from this problem on input G arbitrarily to imagine there's an oracle that tells you I can compute this on arbitrary graph. So the computation of this problem of Z sub AP is reducible to the problem of z sub a. Because if I want to compute z sub ap on arbitrary g, I just change my g to the tp and evaluate z sub a on that g to the p. So the reduction goes from this side to that side, which means that if this is hard, then this is hard. So if this is sharply hard, then this is sharply hard for any p. So the contrapositive says that if this is not sharply hard, then for every p, this must not be sharply hard. So you say you're kicking the can down the street, you don't really have solved any problem, you just pushed one into the other. But the problem, the advantage now the a to the p business is that we have designed this a to the p by this gadget constraint in such a way that a to the p has a very beautiful expression, in particular it's non-negative. And I will ask you just to sort of believe me that this is in fact how the expression will go. It's very simple actually. For a uv assigned to be ij, and then for all possible different values of a and b into between 0 and n minus 1, you will look at how the contribution of, for example, u now is I to c, and a to c. So AIC, and AAC, but that is to be the n minus 1 power, so it's the conjugate. And similarly here for the b part. And then the d, which does not show here, is actually exactly the opposite. You see, this is the conjugate of that, this is the conjugate of that, this is the conjugate of that, and this is the conjugate of that. So it actually gives me the absolute value square. And since I have C1, D1, C2, D2, C3, D3, I'll have P such things, so the whole thing takes the Pth power. If you didn't quite follow that, you just trust me that the right expression for the gadget matrix Aij parameter P is this expression, which in particular is a non-negative. It's a sum of norms. And this can be viewed as a dot product of the two Adama product vectors. So they are all positive because I could take A to be I and B equal to J, and this will be the same as that. So this, in particular, A, one of the m squared terms is actually positive. So the whole thing is positive. And if it's a positive, then the Bulatov-Grove theorem says that the determinant must be 0, and by Cauchy-Schwarz, these guys must be at least as big as those. So in order to be determinant 0, these entries must be the same as this. So in particular now I know that for every I, for every j, this entry is m to the 2p1, which is the expression of aii. Okay, so now I know basically that for every I, for every j, what this value is. Now I'm going to take a different view. I'm going to collect the terms in this expression, which is here, according to the distinct values that this dot product value could occur, and I call them x. X is the value of this as I run the a and b of m squared different things. Now, of course, some value may not occur. I mean, it depends on how many values. Not all the m squared values will be distinct. Nevertheless, take the capital X sub ij to be ij fixed, remember, for the next few slides. Ij fixed, it defines the set of distinct values the x occurs in the sum, and this set is x sub ij. And over the sum, I will say how many times this x occurs among the AB. So this is the number of pairs of AB of m squared such ABs that this particular x occurred. And this gives me a sum of that. Now the number, this x sub s sub x, s sub ij sub x, ij fixed, only depends on x, but doesn't depend on the p. P is outside. The number of times such x occurs among the ABs does not depend on the exponent p. Okay, so this quantity, so far unknown. Of course, the total sum of those quantities will be m squared, because that's the total number of ABs that will equal to some x. But you know, not all m squared things could be different, and I'm going to collect those distinct x sitting there, and then collect the number of x to be like this. Okay. But if you stare at this and imagine that I know this value already, then this looks like a Vandermonde system. Okay, let's look a little closer on the set of different values, this x. These are norms of dot products, so it's non-negative, but these are roots of unities of m terms, so it's a sum of m terms. Each one of them is at most 1 in absolute value, so the sum is at most m. The maximum value is achieved if you take a to the I, a equal to I, b to the j, as we explained before. So we have at least the maximum value m, and the minimum value also appears because of orthogonality. So we know these two values do occur here, and at the moment we don't know if there are other things. Okay, but the value of this is known. And if you look at this as a van der Waals system, then I actually can observe that there is a solution. A particular solution says that for the 0, the x equal to 0 case, I pick this as my unknown, sort of think of this as a van der Waals system where this is unknown variables. These x to the various powers define the matrix of the van der Waals system. The right-hand side is known. If I take these variables, for the 0th one I take this value, for the mth one I take this value, and everything else I take 0 for now, it is a solution. But because this is a van der Waals system, this must be the unique solution. So therefore we know now that no other x occurs. The only value x occurs is the 0 and m, and they occur in this particular multiplicity. Okay? So now we know that this is the solution, and we know this x sub ij for every j exactly solves into these two particular values. So translate back, we say that for every I, for every j, for every a, for every b, this norm sum of the dot product of the two Adama product vectors, the value is either m or 0. Okay. Now let's pick one special case, j equal to 0, which is all one vector. And so this looks like this now. It's the dot product of the Adama product with a row, as all possible a's go. But all possible a's go is the orthonormal basis up to a factor of the norm. So what's called the Parseval's equality in this case will tell me it's basically a triangular equality. It says the hypotenuse square length is the sum square of various orthogonal projections onto the orthogonal basis. Okay, so this is the Parseval equality. It gives me that. And then from this, I can say that the quantity is a sum of m things of quantity squared into m squared by the Parseval. But I already know that every one of those guys is either m or 0. Now, the only way a bunch of things of m or 0 squared sum to m squared is to say that exactly one of them is m, because you cannot have no m. If everybody is not m, then everybody is 0, then this sum is 0. It's not m squared. So it must have at least one m, but it can't have more than one m, because if you have more than one m, the sum is going to exceed m squared. So therefore, there must be exactly one m, and the rest are 0. So now we finally say that it's not just that this is either 0 or m, but for different a's, exactly one a that is m. For all the other a, it must be 0. Okay, so now we know that this dot product norm-wise must be exactly one a is m, and all the other a must be 0. For that a, it's a sum of roots of unities of m terms, and it must sum. The norm is 1, 1, 1, 1, 1 add together. You have m things. Each one of them is a norm 1 thing in the complex plane. It must sum to norm exactly m. Then these norm 1 complex values must be all exactly aligned. So imagine you have origin here, you have a unit vector here, and a unit vector here, unit vector here, but together these 3 unit vectors would sum to length m. All together, it must be that these are all in the same line. So that means that this is an e to the I theta of that. But in the very first entry, these vectors are all 1, so therefore the theta must be 0. So this finally shows that if you give me an I, give me a B arbitrarily, there is an A for which this Adama product is the vector A. And that was the group property that we wish to show. Okay? And I think I will stop here by saying simply that we have made substantial progress in the classification theory. It comes in 3 frameworks of graph homomorphisms, counting CSP, and Holland problems. But there's still a lot of open problems that are waiting to attack. In particular, for example, for Holland problems, most of the problems are on the Boolean domain. Okay, there is a book that I wrote with Shi Chen. We had volume 1 on the Boolean case, and the second volume is in the progress on the higher domain. Those students who are interested in that, I'll be very happy to answer questions and engage you, and I hope you will find this area rather interesting and full of challenge. And this was a quote from Les Valiant on the book. Okay, I'll stop here. Thank you very much.
Thank you, Professor Chai. And let me ask you one question from one of the audience. So the question is, what about the dichotomy for approximate counting in the sense of FP-ROS or FP-TOS? For example, people have already given a dichotomy for counting the third polynomial, but the FP-ROS case is still far from a dichotomy. I wonder what makes this problem so difficult, like counting bipartite independent set approximately.
Yeah, excellent question. Excellent problem. So what I have described here in this talk is about worst case, the classical complexity classification. There's a lot and tremendous amount of interest in trying to get approximate complexity. So when it is sharply hard, the problem could still be approximable, possibly with randomization, possibly with determinism, possibly within polynomial time, sometimes slightly beyond pseudo-polynomial. A lot of interesting work has been done in there, in particular, for example, Ping Yan and Guo Heng have some wonderful theorems in that space. The thing, I think we are still somewhat a little bit away from being able to prove this complete classification theory, partly because maybe there are still very interesting algorithms that are yet to be discovered. When you have some hidden algorithms that are unknown, then it's very hard to prove they don't exist, right? So the classification theorem basically is trying to say that, you know, these are the problems, and I have a complete picture of what its status would be. To the specific question of the bipartite independent set counting, the BIS problem, I think that is, people tend to believe that this in fact lies somewhere in between of NP hard to approximate and PROS or PTOS. By the way, so in the approximate sense, it was perhaps a theorem already due to Stockmeyer that the counting complexity never goes beyond the randomization to NP oracle. So roughly NP hard on the randomized reduction is as hard as it gets. But like, for example, number set. But there may very well be that it's not the case. There are only these two levels. Yeah, it may be even more than 3 levels, who knows. Like, for example, perfect matchings counting on the general graph is still open. Yeah. Thank you for the question. Excellent question.
Thank you, Professor Chai, and thanks the audience who asked this very interesting question. And the time is up now, but we welcome people to send in the questions online, and we will forward it to Professor Chai Jin-yi. Thank you again, Professor Chai.
Thank you very much.